we'll call them back again. All right. So, any questions at this point? What we're going to be doing. All right. We'll jump on in then, in order, what to use for K. And this is kind of fun. It's a question of how to choose a preconditioner. And choosing a preconditioner is kind of fun because it's really more of an art than a science. You get to use your creativity. So I like to call this little bit here the art of preconditioning. So if you remember, what it is that we want, basically, is we want our preconditioner, which I'll call this matrix K here, to be some approximation to the inverse of the Hessian of our problem. Some approximation to it. Where, if you recall, the Hessian is just the second mixed partial derivative of our function at the actual optimal point, which we don't know until we've solved the problem. So clearly we're going to be doing some sorts of approximations here. Like so. And the idea is, well, even if we can't make or even invert the matrix once we've got it, as long as it's some kind of model of, as long as K is some kind of model of the inverse of the Hessian, we will reduce our condition number. And the more we can reduce that condition number, the faster we'll be able to get to the bottom. And here's an example of how you might go about getting that K. I'll just show you in this particular application, but you'll then get a feel, I think, for how kind of fun this kind of thing can be. And it can make a huge difference, as you'll see on the assignment. Okay, so, well, I guess we'd better remember what our first derivative was. Right? So we recall, in our particular application, we had computed the gradient with respect to W of our energy, and it was composed of, there was a projection operator, O, W, U inverse, W dagger. Well, I had been writing it as W hats everywhere. There's going to be a lot of writing, so I'll just skip the hats on the W. Okay. So, respect to our matrix W, and that then applies to the Hamiltonian acting on W, and then there was some final normalization. And, that's how I remember it. It might be nice to write out the different pieces. So there's HW inverse minus O W U inverse, and then another matrix, W dagger H W, multiplying another U inverse like that. And if you recall, U was the overlap between our wave functions, W dagger O W like that. Okay. Now this actually is going to tell us a little, the next line of thought here will tell us some practical issues also about how we're going to carry out this optimization. If you remember what we're doing, we have these unconstrained wave function coefficients W. And we're just minimizing them. And while we're minimizing over those, we allow them to become non-orthonormal, right? They just do whatever it is that they want to do. At some point, though, we're going to get relatively close to the minimum. And as I had emphasized before, we actually spend most of our time quite close to the quadratic part of the minimum, cranking out the next, remaining sets of digits. So what I've found, and you'll kind of see why it does this in the way we construct the preconditioner, is once you get kind of near that minimum, not super close, but kind of near to it, that's a good time to take the wave functions that you have and orthogonalize them and get a nice orthogonal set, orthonormal set, that is going to look kind of like the final solution. Then, of course, we're going to be refining on this thing to get those last few digits out. But as we do that, the wave functions aren't going to be changing all that much, and they're going to be staying pretty much orthonormal. There'll be some small errors, but pretty much orthonormal. So the first idea is going to be that we're going to agree to get, I don't know how you want to call it, kind of close to the min, and then get a good orthonormal set of wave functions. So what that means basically is you're going to take the wave functions that you have and then replace them with the orthonormalizing formula that we have, u dagger OW to the minus 1/2 power. So then you'll have a nice orthonormal set, and that will mean then that u will get updated to this new w dagger OW, which of course has been constructed to give us the identity. And they're going to stay more or less the identity. And the whole art of preconditioning is, well, just making reasonable approximations to capture most of the condition number in your problem. So, okay, well, if I pre-agree to do all that, then my gradient from then on with respect to w will be this same expression, but now I know that u is going to be close to the identity. So it becomes a bit simpler. It's just hw minus ow w dagger hw. Approximately, right? Okay, now we have to take the second derivative of that to get the Hessian. So the Hessian b, right, is basically going to be another gradient with respect to w of this. And now this first term, I think, is pretty clear, right? I've just got one w there, so I'll just have h. That's good. And well, this other term, it's a little messy, right? It's got a whole bunch of stuff in it. I'm just kind of draw a cloud around it. You know, it's got some w's in there, and some o's, and some h's. We really don't know what to do with that. But we're making a preconditioner, so I know what to do with it. What should we do with it? Forget about it. We just want some approximation to the Hessian to the problem. See? I told you this is fun. Okay. So that gives us our second derivative. Now what was h here? It actually had some structure, some definition to it. The Hamiltonian matrix that went along with that expression we derived some time ago had the kinetic energy part, which is minus 1/2 the Laplacian. And then it had some parts that dealt with the potential in real space. It had a structure like this. There was some potential that lived on the grid points. And you had your transforms that applied it point-wise in real space. Well, that's my H. Now, what we would like is a preconditioner so that we can solve, whatever kind of problem we're faced with. We want to do germanium, hydrogen molecule, any kind of material. And as we change the material, what's going to change is this part, whereas this kinetic energy part is always going to stay the same. So since I really don't know what this is going to be, I just get rid of it. Get rid of that. Like so. Now I've got something here maybe I can work with. Let's see here. So we know what the Laplacian is actually. It's got minus determinant of r in it. Still this factor of 2, whatever. And then Laplacian has the diagonal elements of g squared, you might recall. Like that. Okay. So I'm kind of thinking that, this more or less is some model of the Hessian matrix. And K is just going to be the inverse of that. Something else I can throw away now. See if you guys can tell me why it's okay that I do this. I don't feel like carrying these prefactors around. I'll just get rid of that too. Why is that okay? Why won't that mess me up?
Factor doesn't affect the condition of it?
What? Right, when we make the preconditioner here, if I multiply the preconditioner by some prefactor, right, all I want to do is be scaling my search directions by that factor. And my search directions in the end are going to be multiplied by a scalar that minimizes the function. So they're not really relevant, right, to the search direction. So it's just not relevant. to the search direction D, so we can just get rid of that. Okay, so this gives us also now some idea of the condition numbers that we might be preconditioning away. Let's take a look at the range of these vectors G, right? If I've got some box like this, the minimum G vector basically corresponds to something like a wave in my box. My box will have lattice constant R, so G min is going to be something like 2 pi on R. Whereas G max, if I draw a picture of that, as you know, then I'm talking about a wave that is at my Nyquist frequency. So G max will be something like 2 pi on R times some integer. And if you remember the way the aliasing works in the Fourier box, you count out halfway through your Fourier points to n over 2, and then you flip sign and do the negative ones. So the biggest magnitude we'll get is times n, or s, I guess we'd have called the size of our FFT box, s. I'll just put FFT under it to recall what that is. That's like, what was it, let's see, over 2, and for us, I think we had used something like size 60 in the little problem we were doing in the lab. But that number is only going to get bigger if I make a bigger unit cell or if I put more resolution into the problem. And then the condition number is basically the ratio of the maximum to minimum eigenvalue in my Hessian. In this case, it's going to be something like G max squared over G min squared. And then when I take the ratio, the 2 pi on R factors go away. It's like SFFT over 2 quantity squared. 60 over 2 is 30. Squared is 900, or about that. So you can see, because of the way that the kinetic energy operator goes like the square of the resolution in your problem, that you're going to end up with quite large condition numbers like this. It's going to be pretty typical. And this condition number of 1,000 means if I don't precondition this thing, I'm going to need thousands of iterations to get any good precision in the final answer. So we are, with this very simple model, we are actually able to capture a quite wide dynamic range in the condition numbers. So preconditioning with this at least will reduce the kinetic energy as a source of the poor conditioning. And you'll have a chance in the lab to see how well that ends up working. All right, so let's see here. And then I finally have to settle on the final preconditioner, which of course is just going to be the inverse of my model here. So K is going to be this model B inverse, which will be then diagonal elements of, well, we've got an issue now though, don't we? Because the first G vector actually in any cell is always 0. Right? We're basically inverting the Laplacian operator. So we want to put something in there for it. Now it doesn't make sense to put 0 in there because after all, there are a whole bunch of other pieces that we've just thrown away willy-nilly, right? So we just want to put something that's probably the right order of magnitude for our problem. And our natural units are, of course, atomic units, so G0, order of magnitude-wise, should probably be order unity. So I could replace this with 1, G1 squared, G2 squared, G3 squared, something like that. What I actually did on the assignment was to replace it with 1 over 1 plus G squared. We put the different G alphas in there. So you can see at large G, where actually this approximation to the Hamiltonian is pretty good, because you really are just dominated by these high-frequency waves and their kinetic energy. It'll approach 1 over G squared as it should, and then in the lower frequency channels, it just kind of smoothly goes over and will roll over to something, of approximately good order of magnitude. The key point here is not that I get the low frequency G's right, but that I'm properly preconditioning the high frequency behavior. And that's the precondition I will use. Any questions on that? It's kind of fun. Yes?
If you have something like Coulomb potentials that give you custom wave functions and something, does that change the structure of those high momentum modes, or still do you want to do just Laplacian.
Yeah, that's a good point. So it's true that, yeah, if I have Coulomb potentials, I'm going to have cusps, and I will have high-frequency behavior in my wave functions. What the preconditioner's job, actually, to do is to, when you have errors, wherever they are, this preconditioner will kind of heal out on those errors. So it's a question of whether or not you are interested in the final form or your approach to that form, if you kind of see what I'm saying. So you indeed want to use a preconditioner along these lines regardless of what the final form of the wave function is. This just controls how quickly you approach the final solution. All right, good. Okay, so that's the less technical, more fun part, the art of preconditioning. Next question is, all right, how are we going to carry out this line minimization in practice? So, line minimization. And here, once again, I'm going to take advantage of the fact that we spend most of our time near the minimum. So I'm going to develop an algorithm that works quite well when you're down near the bottom. And it may not necessarily work so well until you get into that vicinity. And the approach is going to be, we're going to use something simple, use a simpler algorithm like steepest descents. Right, for which we don't need line minimization, to get somewhat near the minimum. Then we'll turn on the full conjugate gradient. Excuse me. And the idea here is just that, well, if I do that, then I don't have to work on such a fancy line minimization algorithm, which might take some time to develop. Right? It's always a matter of how much human time and how much compute time. And the truth is we don't spend many iterations, even in steepest descents, to kind of get approximately near the minimum in this problem. So it's best just to focus your efforts when you're very close to the minimum and design a simple algorithm that can handle that particular situation. So let's just sketch out what our functional behavior looks like. We'd actually done this towards the end of last time, I believe. I had drawn a sketch for you that looks something like this. I have a function with the values of my function. Let me call this axis alpha. And up here I can define a function f of alpha, which is really just my full function evaluated by different amounts alpha along my given search direction. And we had decided the general appearance of this would be something like so as you go to positive alpha because you've decided to go against the gradient with the positive definite preconditioner. The function will have a negative derivative at that point. And then, of course, if you go too far in alpha, the energy is eventually going to have to come back up like that. And our job is just to find this ideal step point, alpha star, for iteration n. All right, so we have to minimize that function. I think we all know what the analytic condition for that is. We're going to set the derivative equal to 0. And that derivative we can take by the chain rule as the search direction dotted into the gradient of the function at the corresponding step point. And if I made a graph of that, we know that when alpha is 0, we said we were anticipating starting with a negative value for the derivative. And the value here is something we already have, right? It's a search direction dotted with the gradient at my current position, which again we anticipate to be negative. And then as we are heading down, we expect the derivative to decrease in magnitude and come closer up like this so, right? And what we're looking for, of course, is the point where this thing crosses 0. And that's going to be our solution point. Now, in general, when I'm quite close to the minimum, this looks like what kind of a function? What would be a good model for that function? Energy as I move along this line. Yeah, it should be quadratic, right? I'm just taking a section through some very large quadratic form. The general section of that is going to be a parabola. Good. And then the first derivative of that, of course, is going to be linear. Right? So I'm expecting pretty much linear behavior here. You know, there may be some higher order corrections. It might go a little bit off linear, but it's going to basically be linear. So I have a nice, simple functional form here that I can evaluate. I know my function's linear. I know I'm starting here with a given y-intercept, which I can compute. What you guys can suggest to me? How would I try to... I didn't hit my x, did I? How would I try to find that point there? Propose an algorithm for it. Well, I'll give you a hint here, right? If the function's a line, of course, I know how to solve where a line crosses the x-axis, right? I think we can do that, right? Now, to characterize the line, I have one piece of information right now, which is this one value. What other information am I going to need? The what? The slope of the line. All right. So how am I going to get the slope of the line? And I don't feel, by the way, like taking the second derivative of that mess, right? So some people do that. How do I get the slope of the line? Raise your hands if you know what to do. All right, here. Come on.
Find another point?
Yeah! Right. Sorry. The question sounds so simple. It's like, well, on some level, it's like, it's not even high school calculus, right? It's like, what are they, pre-calc, right? But on the other hand, well, sometimes we have to think these things through in a more complex context. Yeah. So let's just compute another point. So we'll go out to some other point. I like to call it alpha trial, right? And then we can go ahead and evaluate my function here at alpha trial, but that's pretty easy, right? F prime at alpha trial is just going to be my search direction dotted into the gradient, evaluated at this point when I've gone out a distance alpha trial. Let me just call that x trial, where x trial, of course, is just xn plus my alpha trial step size times my search direction n. Good. Now I've got 2 points on a line. I think we can handle the problem of, I wish I had drawn through the point, but whatever, calculating where that thing crosses the axis. And there's like a million ways to do that. I like to, I don't know, let's do the way where we compute the slope 2 different ways and set them equal, right? So one slope we know is certainly the one from our trial step, right? We know the slope would be f at alpha trial minus f at 0, sorry, f prime, right? Because we're looking at the derivative function, divided by, well, whatever, the change in the x-coordinate. And that should then equal the difference at the point where I want some information, f at the solution point minus, again, this is f prime at 0, divided by the solution point, which I wish I knew, minus 0. And then, well, we can proceed along pretty nicely. We can compute this number. We have this number. It's something we know. F prime at alpha star n is, of course, 0, because that's what we're looking for. Okay, and then we know this one, and we want that one, so we can solve this. Alpha star n, that is going to be, well, I'll move this over to that side of the equation, where it'll show up on top. On this side of the equation, I'm going to have minus derivative at 0, right? This one will come on top when it goes over there, so everything's proportional to alpha trial. That sets the scale, that makes sense. Then divide by this denominator, f prime at alpha trial minus f prime at 0. And then I guess just to make it all complete, alpha trial times. Okay, f prime at 0 was the search direction dotted with the gradient at the starting point. That minus sign I'll combine with this one. So f prime of 0 again is dn dot grad f at the starting point, and then minus, because I pulled the minus sign down, the trial derivative, which of course is dn dot the gradient at the trial point, x trial. Where x trial, as we said, was the starting point plus the trial step times the search direction. And that's a quite robust algorithm, as you'll see. Very simple. But gets the job done. Right? Why make something more complicated than you have to? Particularly when that usually creates bugs. Good. All right, questions there? Yes?
How do you choose alpha trial?
Smart man. Well, I don't know. Should I ask these guys here? Well, any thoughts, folks? I'll tell you what I do. Well, first of all, should alpha trial matter much?
It should be near the minimum, so that it's the.
Right. This evaluation, to the extent that this is linear, the answer will be independent of alpha trial. So to some extent, it's fairly insensitive. Now, what are you trading between them? There's a sweet spot, so to speak. Well, if you have too tiny an alpha trial, then this difference will start getting close to machine precision, and you won't have many significant figures when you evaluate that difference. So you don't want alpha trial too small, right? It's going to sound like Goldilocks answer, right? So you don't want alpha too small. On the other hand, you don't want it too big, because if it's too big, you'll step out of, sort of the quadratic range of the function. So you have to be careful with it. And as you run the code, you'll gain some experience with this. Generally, what I tend to do is, first, as we said, we're going to start with steepest descents, right? Just to kind of get us kind of somewhere near where we can turn on the more advanced technology here. And while you're doing that process, you are going to have to play around with alpha, right? Again, if you make it too small, you'll be going nice and downhill, but you know it's taking forever. So you're going to increase alpha, right? Until you're converging very quickly, and then all of a sudden you notice, wait, the energy's going up, so you'll cut back on alpha. So when you're doing the steepest descents parts, you're going to get some sense for how big alpha should be. Then what I generally find, for just fixed step sizes. And those fixed step sizes, generally, the alphas that do that, will tend to step you somewhere down here towards the bottom of this parabola. So that's not a bad one to use. So I'll just use the alpha. For alpha trial, I'll just use the successful alpha from the line minimization. That's a practical answer. I guess a theoretical answer is, well, if you think carefully here, likely alpha should be all the prefactors I dropped off of my precondition, or related to it that way. But for some reason, the practical approach seems to work the best here. Yes?
Also, this will work only if alpha equal to 0 lies in the quadratic region.
If alpha, you're saying if xn is not in the quadratic region, this isn't going to work? Yeah, I agree. So we want to make sure we get down into the quadratic region. In this particular case, for every electronic structure calculation I've ever done, in whatever basis, it turns out steepest descents, it depends on the system a little bit, but maybe 20, 30 iterations of steepest descents get you close enough that you can flip on the quadratic algorithm, right? And then you do another 100 to get all your precision. But that's a practical answer. So fair enough. If we didn't have that luck, then we'd have to think about some more advanced algorithms to get close. Okay. Other questions, comments? All right. So I think you guys can do the minimizations. Good. Okay, so then you're all set for the upcoming problem set. Now there's that little subtlety. No, that gets you set for the last do problem set, for problem set 3, where you do the advanced minimization. There's one little detail left over for the currently due problem set, which I'd like to discuss a little bit, and that is the issue of getting eigensets. And I mentioned that there's an interesting symmetry in the density functional theory energy functional that complicates this extraction of eigenstates. So let's kind of remind ourselves of what that energy function is and see where this symmetry gets us into a little bit of trouble. So you may recall that my energy function, I'll call it DFT just to kind of remind you what function I'm talking about here, but just a good old energy function, had the following structure to it. The kinetic energy had, well, there's something proportional to the fillings, but then there was the trace of the kinetic energy operator, which is 1/2 the Laplacian in our units, times the density matrix, where this density matrix was the outer product of C, our expansion coefficients in our basis. Plus then, it had some other stuff, which is all written as a function of the density. And the density itself had, some filling prefactor on it. And then again, it too could be written in terms of the density matrix, where there was a transformation of the density matrix into real space within the usual, post and multiplied by the transformation matrix, same thing. That was our density. So the entire energy function comes down to a dependence upon this single particle density. Now, we'll come back to it, but I'm just curious if anyone can pick it off right away. What set of transformations can I make, then, on my wave functions that would leave this energy invariant? I'll let you think for a second. I'm going to tuck my shirt in.